If you like WebAssembly and you like reading extremely complicated topics that are easy to consume in cartoon form, then you may have seen work done by Lynn, the first speaker. She'll be joined by Till Schneidereit. Till Schneidereit works on all sorts of tools related to WebAssembly. Some of his team is here too, and they are going to be talking about WebAssembly's post-MVP future. And without further ado, I will hand it to Lynn and Till.
Thank you, Jonathan. And we're just going to take a little moment to get set up here. Let's see. Okay, everybody. Hi, I am Lynn Clark, and I make code cartoons. And I also work here at Mozilla. I work on things like WebAssembly, which, of course, we're all here to talk about. And I'm joined in this talk by Till. He leads our WebAssembly tooling efforts at Mozilla, and he'll be filling us in on some of the work that that team is doing as well. So first off, what is WebAssembly? Since you're here, you probably already know this, but it's a way of running programming languages other than JavaScript on the web. Up until now, if you wanted to run code on a web page, the only language that you could use was JavaScript. But now there's WebAssembly, and that means that you can use other languages like C and C++ and Rust. I wish I had time to go into more detail about how this all works under the hood, because it is pretty fascinating, but this talk is so jam-packed with content, I don't have time to cover what's already in the browsers. And in fact, I don't actually have enough time to really go into too much detail about what's in the talk. But if you want more detail on this stuff, you can check out the code cartoons on hacks.mozilla.org, including the post that inspired this talk that does go into more detail. My first articles about WebAssembly came out when WebAssembly was first turned on by default in browsers. You might have seen them. This is one of the illustrations from them. But then, since then, I've noticed that some people have a misconception about WebAssembly. They think that the MVP that landed in browsers in 2017 is the final version of WebAssembly. And I can understand where this misconception comes from. The WebAssembly community group is really committed to backwards compatibility. So the WebAssembly that you write today will continue working long into the future. But that doesn't mean that it's feature complete. And in fact, it's far from the case. Features are coming to WebAssembly which are going to fundamentally alter what you can do with WebAssembly. So I think of these features kind of like the skill tree in a video game. We fully filled in the top few bubbles, the top few skills in the skill tree, but there's still this whole tree below that we need to fill in. So let's look at what's been filled in already, and then we can see what's yet to come. So WebAssembly's story starts with Emscripten, which made it possible to take large existing C++ code bases and for things like desktop applications and bring those to the web. And it did this by transpiling that code to JavaScript. But the JavaScript that it automatically generated was still pretty slow, and it was slower than it would be as run as native code. A stroke of insight fixed this, though. One of Firefox's JavaScript engineers figured out how to make this JavaScript run fast. And that gave us Asm.js. So it's just a little optimization in the engine. Once the other browser vendors saw how fast Firefox could run Asm.js, they started adding the same optimizations to their engines. But that wasn't the end of the story. It was just the beginning. There was still many things that the engines could do to make this faster. But they couldn't do it in JavaScript itself. Instead, they needed a new language, one that was designed specifically to be compiled to, and that was WebAssembly. So what skills were needed for the first version of WebAssembly to get to that minimum viable product that could actually run C and C++ on the web? WebAssembly's designers knew that they wanted to support languages besides just C and C++, so they needed a language-agnostic compile target. Something like the assembly language that things like desktop applications are compiled to, like x86. But this assembly language wouldn't be for an actual physical machine. It would be for a conceptual machine. That compiler target had to run very fast in order to meet users' expectations for smooth interactions and gameplay. It also needed to load fast, because the web users are used to fast load times, reasonably fast load times at least. But these kinds of applications are pretty large code bases, which means that there's a lot to download and compile when the user first goes to that URL. So we needed the compile target to be compact. That way it could go over the internet quickly. These languages also need to use memory differently from JavaScript. They need to be able to directly manage the memory. And this is because languages like C and C++ have a low-level language feature called pointers, where you actually have memory addresses that you can read and write from. But you can't have a program that you downloaded from the web just willy-nilly going into your memory and changing things at different memory addresses. So in order to provide a way to access memory like a native program is used to, but to keep the browser secure, there needs to be something that could give access to a very specific part of memory and nothing else. To do this, WebAssembly uses a linear memory model. And this is implemented using typed arrays. So basically, just a JavaScript array, except this array contains bytes. So when you're accessing it, you're just using array indexes, which you're treating as if they were memory addresses. And this means that you can pretend that this array is C++ memory. So with all of those things in place, you could run desktop applications and games in your browser as if they were running natively on your computer. And that was pretty much the skill set that WebAssembly had when it was released as an MVP. It truly was an MVP. It was a minimum viable product. It allowed certain kinds of applications to work, but there was still a whole host of other applications yet to be unlocked. So the next achievement to unlock is heavier weight applications. Can you imagine if something like Photoshop were running in your browser, if you could have it pull it up on all different devices, work on your files, no matter what device you're using? We've already started seeing things like this. For example, the AutoCAD team has made their CAD software available in the browser. And Adobe has made Lightroom available through the browser using WebAssembly. But there are still a few features that we need to make sure that all of these applications, even the heaviest of heavyweight applications, run well in the browser. So first is support for multi-threading, because modern-day computers have multiple cores that can process things in parallel. But to make use of those cores, you need support for threading. There's another bit of modern hardware that processes things in parallel, and that's SIMD, single instruction multiple data. So with SIMD, it's possible to take a chunk of memory and split it up across different execution units, which are basically light cores. And then you have the same bit of code, the same instruction, run across all of those execution units, but they're all acting on a different part of the data. Another hardware capability is 64-bit addressing. So memory addresses are just numbers, and that means if your memory address only has 32 bits in it, you can only have so many memory addresses, about 4 gigabytes. But modern hardware supports 64-bit addressing, which offers 16 exabytes of memory addresses, and that's a big difference. Adding 64-bit support will take the artificial limitation on address space out of WebAssembly. But these applications don't just need to run fast. Load times need to be fast too. So one big step here is streaming compilation, compiling the WebAssembly file while it's still being downloaded. And WebAssembly was designed for this. In Firefox, we compile it so fast that it's basically done compiling by the time it finishes downloading. And other browsers are adding streaming as well. A tiered compiler also helps. So in Firefox, we have 2 compilers. The first one, the baseline compiler, kicks in once we start downloading the code, and it compiles the code quickly. The other compiler, the optimizing compiler, runs on several threads in the background. And this one takes longer to compile, but it generates extremely fast code. So when that's done compiling, it'll swap out its extremely fast code for the previous one, which is pretty fast, but not as fast. We're also working on a new optimizing compiler called CraneLift. And so CraneLift was designed to compile faster than our current optimizing compiler. But the code it generates is still very fast. And we're currently working to see if we can make it generate code that's even faster than our current optimizing compiler. There's an even better trick that we can use, though, to skip compiling most of the time completely. Unlike JavaScript, if you load the same assembly file twice, it will compile to the exact same machine code. So we can store that compiled code in the HTTP cache. And that means when the browser goes to try and fetch that, it'll check the cache first. And instead of pulling out the WASM file that then needs to be compiled, it'll pull out the compiled bytecode instead. So this skips compiling completely. And there are other ways to skip even more work. So stay tuned to see what else is happening with improving load times. Where are we with supporting these heavyweight applications right now? For the threading, we have a proposal that's pretty much done, but a key piece of that, shared array buffers, had to be turned off in all of the browsers early last year. But those are coming back soon. SIMD is under active development at the moment. And WASM 64, we have a good picture of how this will work. It's going to work pretty similar to how x86 or ARM got support for 60-bit addressing, but it's not currently underway. For the streaming compilation, we added our streaming compiler last year, and other browsers are currently working on their implementation of this. We also added our baseline compiler, and other browsers have been adding the same kind of tiered compilation over the past year. In Firefox, HTTP caching is close, and other improvements are in discussion. Even though this is all still in progress, heavyweight applications are already coming out today because WebAssembly already gives these apps the performance that they need. But once these features are all in place, that's going to be another achievement unlocked, and more of these heavyweight applications will come to the browser. But WebAssembly isn't just for these heavyweight desktop applications. It's also meant for regular web development, the kind of web development that you're used to, small modules web development. So if you have a module that does a lot of heavy processing, a lot of computation, that's probably a good use case for WebAssembly. And again, we're already seeing some of this happening. So for example, there's the parser in the source map library that's used in Firefox's DevTools and in Webpack. That was rewritten in Rust, compiled to WebAssembly, and it's now 11 times faster. And the Gutenberg parser in WordPress is now an average of 86 times faster after their rewrite in Rust compiled to WebAssembly. But for this kind of development to go mainstream, we need to have a few more things in place. First, calls between JavaScript and WebAssembly need to be fast. When WebAssembly first came out, these calls weren't fast because, it was an MVP. The engines made it work, but they hadn't optimized it yet. We finished our optimization work on this in Firefox last summer, and now some of these calls are actually faster than non-inline JavaScript to JavaScript calls. That brings us to another thing, though. You often need to pass data between your JavaScript and WebAssembly functions. So you need to pass in values and return values out. This can be slow, and it can be difficult, too. At the moment, WebAssembly only understands numbers. So this means that you can't pass more complex values like objects in as parameters. You need to convert that object into numbers and put it into the linear memory. And that's kind of complicated, and it takes time to do this conversion, to convert the data into the linear memory. So we need this to be easier and faster. We also need to integrate with ES modules. Right now, you can't use import and export syntax to import a WASM module into your app. But that means that the WebAssembly module isn't really part of the JavaScript module graph. Just being able to import and export doesn't get us all the way there, though. We also need ways to distribute and bundle WebAssembly modules. What's the NPM for WebAssembly? What about NPM? What's the Webpack or parcel for WebAssembly? Well, what about Webpack or parcel? These modules shouldn't look any different to the people who are using them, so no reason to create a separate ecosystem. And there's one more thing. Support for older versions of browsers, even those that don't know what WebAssembly is, like IE 11. So where are we on all of this? Calls between JavaScript and WebAssembly are fast in Firefox now, and other browsers are also working on this. For easy and fast data exchange, there are a few proposals that will help with this. There's the reference types proposal, which makes it possible to use references as arguments and return values. And these are references to objects from outside of WebAssembly, so objects from JavaScript, for example. There's another proposal, the host bindings proposal, which will make this even faster. And another thing that we can do to make things easier is help dealing with memory, because right now, if you have some data that you have put into linear memory that you need JavaScript to use, that JavaScript code actually has to free that memory after it's done with it. But with the weak refs proposal, you'll be able to do a little bit of automation to make this happen without having to call free right afterwards. So these proposals are all in flight. In the meantime, the Rust ecosystem has created tools that help handle this all with Rust code. For ES module integration, the proposal is pretty far along. For toolchain support, there are tools like WASMPack in the Rust ecosystem, which automatically runs everything that you need to package your code for NPM. And the bundlers are also actively working on support. Finally, for backwards compatibility, there's the WASM2.js tool. That takes a WASM file and spits out the equivalent JS. Now, this JS is not going to run fast, but at least it means that your WebAssembly code is going to work in these older browsers, the ones that don't understand what WebAssembly is. Once we unlock this achievement, we open the path to another 2 achievements. One of them is rewriting large parts of JavaScript frameworks in WebAssembly, and the other is making it possible for statically typed compile-to-JS languages to compile to WebAssembly instead. So these are languages like Scala.js or Reason or Elm. For both of these use cases, WebAssembly needs to support high-level language features. So first, let's look at rewriting parts of JS frameworks. For a framework like React, you could parallelize the DOM diffing algorithm, the virtual DOM algorithm, with a language that has really good ergonomic support for parallel code, something like Rust. And you could also speed things up and reduce memory usage by allocating memory differently. But you still need to interact with JavaScript objects, things like the components that the users are writing from that code. You can't just write everything in linear memory because that would be difficult and inefficient. So you need to be able to integrate with the browser's GC at the same time. Some of the JavaScript objects are going to need to point to linear memory, and some of the linear memory is going to need to point to JavaScript objects. If this ends up creating cycles, it can mean trouble for the garbage collector. So WebAssembly needs this integration with the GC to make sure that all kinds of cross-language data dependencies can work. And this will also help the languages that compile to JavaScript, like Scala.js, Reason, and Elm, because these languages use JavaScript's garbage collector when they compile to JS. And that's the same garbage collector that WebAssembly running in the browser will use. So these languages won't need to change how their GC works. We also need better support for handling exceptions. Now, most WebAssembly modules today don't currently support exception handling. You can turn it on, but most don't. But JavaScript has exceptions. So even if you've compiled your code not to use exceptions, JavaScript may throw one into the works. If your WebAssembly function calls a JavaScript function that throws, then it's likely that the WebAssembly module won't be able to correctly handle that exception. So we need to make that work better. We also need good debugging support. DevTools make it easy to step through JS code today in the browser. We need that same level of support for WebAssembly. And finally, for many functional languages, you need to have support for something called tail calls. So where are we on all of this? For garbage collection, there are 2 proposals currently underway, the typed objects proposal for JavaScript and the GC proposal for WebAssembly. And our team already has a prototype of these working. But it's still going to take some time for these to go through the standardization process. So we're probably looking at sometime next year. Exception handling is still in the research and development phase. For debugging, there's currently some support in browsers, but it's not ideal. So there's a subgroup of the WebAssembly CG that's working on specifying that. And the tail calls proposal is underway. Once those are all in place, we'll have unlocked JS frameworks and many compiled to JS languages. So these are all achievements that we can unlock in the browser. But what about outside of the browser? Now, you may be confused when I talk about outside of the browser, because isn't the browser what you use to view the web? And isn't the web right in the name, WebAssembly? But the truth is technologies like HTML and CSS and JavaScript are only part of what makes the web. They're the visible part. They're what you use to create your user interface, so they are the most obvious part. But there's another really important part of the web which has properties that aren't as visible, and that is the link. The link's innovation is that I can link to your page without having to sign up for any registry or ask you or even know who you are. It's this ease of linking that enabled us to form global communities with people we didn't know. But there are two problems here that we haven't addressed if we just have this link. The first one is you go visit the site and it delivers some code to you. How does it know what kind of code it should deliver to you? Because if you're running on a Mac, then you're going to need different machine code than if you're on Windows. That's why you have different versions of programs for different systems. Does a website need a different version of the code for every possible device? No. Instead, the site has one version of the code, the source code, and that's delivered to the user. And then it's translated to machine code on the user's device. The name for this concept is portability. With it, websites don't need to know what kind of device you're running. But that brings us to a second problem. If you don't know these people whose web pages you're loading, how do you know what kind of code they're giving to you? It could be trying to take over your system. Doesn't this vision of the web, running code from anybody whose link you follow, mean that you have to blindly trust anyone who's on the web? This is where the other key concept from the web comes in, and that's the security model. Basically, the browser takes the code and puts it in a sandbox, and it gives it a couple of toys that it can use to do interesting things and have an effect on the outside world, but it leaves the dangerous toys outside of the sandbox. So the utility of the link is based on these two things. Portability, being able to deliver the same code to any device and have that run on that device, and the sandbox, the security model that lets you run this code without putting your machine at risk. So what difference does it make if you think of the web this way? It changes how you think about WebAssembly. You can think about WebAssembly as just another tool in the browser's toolbox, which it is, but it's not just that. WebAssembly also gives us a way to take these two capabilities of the web, these key capabilities, the portability and the security model, and bring them to other use cases that need them too. We can expand the web past the boundaries of the browser. Now, you may be thinking, this already happened with Node.js. But as it is today, Node doesn't quite get us there. It doesn't give us full portability, and it doesn't give us the same security, the same ability to run this untrusted code either. With Node, it's possible to run JavaScript on servers and other devices without a browser. So that does give us some portability. But you still need native modules in a number of cases, either because the native code performs better, or because you've already written something in a language like C or C++ and you want to reuse it. The problem is native modules aren't portable. They have to be compiled specifically for the user's device ahead of time. We're also still missing security. Node could have taken the sandbox from the browser, but Node made the design decision early on that JavaScript modules would have full access to system APIs. So JS modules can do things like read and write files on your machine. These capabilities, things like full direct file access, are the dangerous toys that aren't available in the browser sandbox. Even though they are dangerous, for the kinds of use cases that Node is addressing, the kinds it was built for, this kind of access does make a certain amount of sense. The thing that I really want to make clear here is that Node made a choice. And really, it's that Node had a choice to make. For JS modules, it could have gone with a sandbox-style approach. But for native modules, Node didn't really have a choice because it's hard to sandbox native code. For Node, this is really a moot point. These design decisions have been made, and if you're running a Node application on your computer, you basically said, I trust this code. But what about other use cases? Wouldn't it be nice to have the portability and the security of the web? WebAssembly makes this possible. WebAssembly starts with the advantages of JS, this portability and the ability to be sandboxed, and what it adds is performance. And that means that developers don't need to resort to this native code that's hard to sandbox. So this means that we can bring portability and security to use cases outside of the browser. Use cases from the cloud to the blockchain to the Internet of Things. And Till will talk more about how it does that in a second. But first, I want to finish up with Node. Because even though Node has no use for WebAssembly's ability to run untrusted code, WebAssembly can still help Node. So how can we improve Node using WebAssembly? We could bring full portability to Node. We could eliminate most need for native modules, ones that are compiled for the user's device ahead of time. These could be written in WebAssembly instead and just compiled once. And then they could run across all devices just like the JavaScript modules in Node do. The only problem here is that WebAssembly doesn't have direct access to the system's resources. We need to pass in functions so that it could work with the operating system. For Node, this will probably include a lot of the functionality that's in things like the C standard library and things that are part of POSIX, the Portable Operating Systems Interface. That's an older standard. It provides an API for interacting with the system across a bunch of different Unix-like OSs. To make this happen, the Node core folks would need to figure out what API they want to expose here, what API they want these functions to have. But wouldn't it be nice if that were actually something standard? Not something that was constrained to just Node, but could be used across other runtimes and use cases too. So maybe a POSIX for WebAssembly, a POSIX, if you will, a portable WebAssembly system interface. And if it's done in the right way, you could even implement the same API, but in a different way for the web. Now, these functions might not be part of the WebAssembly spec, and there would definitely be WASM hosts that wouldn't have them available. But for those platforms that could make use of them, there would be a unified API for calling these functions, no matter which platform the code was running on. And this would make writing universal modules, those that run across both the browser and Node, so much easier. So, is this something that could actually happen? Well, Till will fill us in a little bit on that.
Thanks. Well, we and others are working on it, and I think we have a pretty good chance. Apologies. I will talk a bit about developments in this space, but before I go to that, I do want to say a bit more about some of the use cases that this will unlock.
Could you speak even more directly?
Even more directly. Okay. One of these use cases is the domain of CDNs and of serverless and edge computing. Increasingly, CDNs want to run code on these edge machines instead of just serving static resources, something that historically only servers used to be able to do. But the CDN just works at a different scale, where a traditional server might process hundreds, perhaps thousands of requests per second. A single machine in a CDN has to go an order of magnitude higher, have tens of thousands of requests per second easily. WebAssembly allows the Fastly CDN that serves a significant fraction of the Internet's traffic to run user code at this kind of scale. And to get there, they're using WebAssembly in fascinating ways. Luckily, I don't have to go into the details of this tonight because we have Tyler McMullen, their CTO here, who will give a talk about some of the tricks they employ to get to this massive scale after we finish up here. But for this talk, the point is they didn't just need scale, they also needed the speed that WebAssembly gives compared to a scripting language like JavaScript, and the safety. And so they didn't just need to get to this scale. They needed to do some other things to make this work. So what are some of these other things? Well, at a basic level, their customers want to run code in response to network requests. So even more fundamentally, their code needs to talk to the outside world. In a browser, if you were to use WebAssembly, this is done through JavaScript, because in the browser, you always instantiate a WebAssembly module through JavaScript around it, and that JavaScript provides it with functions that it can use to talk to the outside world. But at Fastly, they are not using JavaScript. They are only using WebAssembly, and so they needed something else. They needed to create their own runtime, which in this case means taking a WebAssembly compiler, something that takes the WebAssembly bytecode and compiles it down to machine-specific code for that specific machine, the CPU architecture that it's supposed to run on. And then adding some functions for doing some fundamental tasks, such as memory management and talking to the outside world. Functionality like this is, as Lynn mentioned before, commonly provided by a standard library. At Fastly, for the WebAssembly compiler, they are using the one we are developing at Mozilla called Brainlift, which Lynn also mentioned. And it's pretty fast and small and self-contained, so you don't get large additional code bases as dependencies for your projects. And we are also integrating it into Firefox, so we are working hard to make sure it's not only fast, but also safe. Now, for the runtime environment, they had to create their own, because there is no standard for this yet. They essentially had to figure out what is exactly our use case, what are our requirements, and then do all the hard work to figure out what do we need to expose, how do we expose it, how do we make sure it is safe. And so this is all possible today, but it is a lot of hard work, and it takes an exceptional team to pull this off right now. Nevertheless, there are actually a lot of runtime projects out there. There is a lot of movement in this. It is still a very young area, but there are literally dozens of different projects trying to make this work. And I'll just mention a few of them, like WAVM, which is based on the LLVM compiler toolchain that also powers the Clang C and C++ compiler and the Rust compiler. And WASMJIT, which I'll once again mention briefly later on because it does some very interesting things. And same as Fastly, we are also working on a runtime based on Brainlift. It's called WasmTime. And if you want to learn more, find me after the talk, or even better, talk to Dan Goman in the back there, who is the lead of that project. So with a runtime like this, we can address not only the CDN use case, but also a whole range of other use cases. And I'll just briefly mention a few of these. People are working on building blockchain platforms with WebAssembly, where you write smart contracts in a language and compile it to WebAssembly and run it in the safe sandbox. There's interest in the IoT space for making use of both the portability and the sandboxing aspects. And there's interest in writing portable CLI tools with WebAssembly. We've also seen some interest from companies building game engines where WebAssembly can serve as essentially the scripting engine, where currently they might use Lua or JavaScript. But this would free them to make use of all languages, or all those that compile to WebAssembly at least. And with projects like WasmJIT and Nebulet, some folks try to make WebAssembly run inside the kernel of operating systems. And this is a really interesting use case because it's a domain where WebAssembly can actually be faster than native code. Because nobody should ever run something, essentially user code, in a kernel without a proper sandbox. That is, you shouldn't do that. But that means for workloads where you have to do a lot of calls into and out of the kernel, you have this overhead switching between user space and kernel space. And that overhead can, for certain use cases, be higher than the overhead that WebAssembly has. So for these use cases, running in the kernel in the WebAssembly sandbox can actually be faster. We talked more about all of these very different environments and use cases in a blog post that Lynn mentioned earlier, the post MVP Future of WebAssembly on hacks.mozilla.org. It was published back in October. So if you want to learn some more about these use cases and environments, you should read that post. One aspect I want to go into some more for tonight is portability. And this sort of goes both ways. It's not only about portability in that the same compiled code should run on all kinds of architectures, but it's also about sort of sussing out commonalities between different use cases and ensuring that you only have to write code once and have it work for all these different use cases. Now for JavaScript, a big part of this portability is provided by, well, the language itself. The fact that there are a lot of modules, a big chunk of functionality that you can effectively implement by just sticking to the language itself, instead of having to rely on features that the runtime environment might add for you. And another part, so this is true for code that runs both in the browser and in Node. But another part of portability across different use cases is provided by the fact that there is a dominant runtime. Turns out if you're running code outside the browser, chances are you're going to use Node. And that means there's a set of APIs that you can rely on being available because Node has them. There's no standard for this, but there's a de facto standard. So it's sort of portability through sheer dominance. If we had a standardized runtime environment, this POSIX Lynn mentioned, then we could get something that is effectively similar. We could get the ability to rely on these APIs being available no matter what your exact use case is, but in a way that's not a one-size-fits-all. Because turns out one-size-fits-all usually means it doesn't fit anybody really that well. And we want to get to a future where there are a lot of different runtimes that work well for specific use cases. And still, you can target all of them if you don't have, for the parts of your code that aren't just very specific to your use case, you should be able to just say, okay, there's this set of APIs that'll just be available. So for the standard library, we could say, yeah, let's just use POSIX and be done with it. Because that is easy to do, and it's sort of, it makes porting to the platform also about as simple as can be. And runtimes like WAVM do, in fact, do something very similar to this. So as I said, it's fairly easy to do, leads to good ways to porting to it. So what's not to like about that? Unfortunately, it eliminates one of WebAssembly's big advantages, and that is the security model, and in particular, the sandboxing. Lynn talked about how Node had a choice to make, for the JS modules at least. A choice between keeping the sandbox that JS runs in the browser, or giving it an easy way to talk to the outside world. And we now have the same or a very similar choice to make, but for WebAssembly. Do we go with this easiest route, but give up on sandboxing? Or do we do something different? Something that allows better control and leads to better security and auditability. And that last part is, I think, really important. If you look at an application, you should be able to see what it could possibly do to your system. Not what is it coded to do, but what kinds of permissions does it have? What's sort of the worst case it could do? Look at the label instead of the implementation in detail, and then decide, do I want to run this? Can it steal my Bitcoin wallet? Maybe not run that code. But can it only operate in this current working directory and process a file I give to it and then spit out a result in that same directory? That's probably fine. So you should be able to do that. You should be able to, without deeply investigating what it really does, figure out, do I trust this enough to run it or not? With POSIX, that is incredibly hard, or really almost impossible, but you have to employ operating system-specific sandboxing mechanisms. And these are specific, again, to operating systems, so there goes a significant part of your portability. And even though, if nothing had changed since Node was created, chances are we would go with the same decision they made, because what they did made sense. Because designs that lead to the security and auditability, but still are easy enough to actually use in the real world, those existed, kind of, in academia. But they hadn't really been tested in the real world and at scale. Luckily for us, things have changed, and these designs exist, and they are being tested in the real world. For example, Google is building the Fuchsia operating system around just such a design. And for WebAssembly, we are working on a standard library that will make it easy to build secure, auditable, and portable modules and applications that will work for all of these use cases. So with this standardized API, you could get the same flexibility that you have with Node, but still have security and auditability. And you can run the same code in a variety of runtimes, such as WebAssembly, Node, and the browser. With all this, it is still vitally important that you have the same ease of use. And that starts with the tool chain you use. You should be able to use a fairly standard tool chain to target this environment without having to jump through hoops. Initially, we're focusing on seamless support for the Rust ecosystem, bringing not only code you write specifically for this target, but most of the Rust ecosystem with its Crates.io-based sort of NPM-like packages to this platform. But we actually also have code running already for C and C++, and other languages will be supported as well eventually. Lynn also mentioned that browser vendors are working on good DevTools support for WebAssembly. And this, of course, is really important. You need to debug your code. For WebAssembly running outside the browser, we believe that the same is important. You need to be able to use the DevTools you're used to, the debuggers you're used to. And so for Brainlift and WebAssembly, we are working on making it possible to use debuggers like LLDB and GDB, and the IDEs, perhaps even more importantly, the IDEs using them under the hood, such as Xcode and Visual Studio Code. So as you can see, there's a lot of development going on in this space, and we are all working hard to make it easy to target these use cases without having to jump through hoops and with easy debuggability.
Okay. Now let's zoom back out and look at the skill tree again. I said in the beginning of this talk that people have a misconception about WebAssembly. This idea that the WebAssembly that landed in the MVP is the final version of WebAssembly. And I think you can see now why this is a misconception. Yes, the MVP opened up a lot of opportunities. It made it possible to bring a lot of desktop applications to the web. But we still have many use cases to unlock. From heavyweight desktop applications to small modules to JS frameworks and to all of the things outside of the browser, things like Node and serverless and the blockchain and portable CLI tools and the Internet of Things. So the WebAssembly that we have today is not the end of the story, because WebAssembly still has promise to keep and many places to go before it sleeps. Now, before I finish up, I just want to give a little bit of thanks. I really enjoy working at Mozilla because I get to work on exciting things like WebAssembly, but I also really enjoy it because I get to work on engaging problems with some very smart and very interesting and very kind people. And I had a chance to collaborate with 2 of them on this talk. So of course, one of these is Till Schneidereit, and the other is Luke Wagner, who is one of the co-creators of WebAssembly's and was a major driving force in making WebAssembly happen as well. So thank you to both of them. And thank you all for listening.